All right, let's get started. Welcome back, everyone. Today, Zhuk will tell us about clones on 3 elements and New Hope. Please.
Yeah, thank you very much for the introduction, for the invitation. In pandemic time, I hated that all talks are online, but now it's kind of fine. You can see people from around the world. My talk is on the same topic as Albert's talk 2 weeks ago. I want to apologize for a significant intersection, but Albert's talk was like a proper mathematical talk with definitions and theorems and everything, and I will try to give more emotional talk, just show you many examples and my view on the subject. Okay, so I will have some introduction, and then for 6 parts, as in Star Wars, I don't really respect the last 3. Let me start. Why clones? Because clones are really wonderful. If you look at the definition, it's very simple, just set of operations closed under composition. You can easily explain the definition even to a non-mathematician. And if you look at the examples like clone of monotone operation or clone of linear operations, it's clear that there is something fundamental in them. They're very nice and interesting. Some other examples of clones are clone of unary operation, clone of dual operation, or Slupetsky maximal clone. And we know that clones ordered by inclusion for a fixed domain form a lattice. And as I said, today I want to show you many examples of lattices and of clones. And that's my first example. You can see lattice of all clones on element domain containing operation x plus 1. And this is a very nice exercise. You can easily give this exercise to a student, and I promise you that they will enjoy getting started. Like here you can x plus 1, at constant 0, here you add 2x, and now you have all permutations, element domain, and so on and so on. And even in this small lattice, you have very nice examples of clones and algebras. For example, this L2 is very nice because it's like linear operation model 2 still inside element domain. So this one is wonderful. This is the maximal clone of linear operations and two operations. My point is that even if you consider this very simple example, starting with x plus 1 operation, you get very nice clones. And it's also very easy. Like you can easily explain what's going on here to a student or even student from high school. Okay, another example of such a lattice is the lattice of all clones containing into x plus one element domain. Also very simple and very nice. But of course, the most popular lattice is post lattice. Here you can see the list of all clones on 2-element domain. And I'm pretty sure that anyone who ever worked with this lattice really love it because like using this lattice, you can take any operations on 2-element domain and you can calculate what you can derive using composition. So it's like 100 different small theorems are hidden inside this one picture. So it's really wonderful. And of course, I have to mention Galois connection. We can define these two operators inf and pol. Okay, I will show you like this. And then we have a one-to-one correspondence, very natural Galois connection between clones and relational clones. So we connected two fundamental objects, operations and relations. And this connection is really nice. We have composition, like one operation, natural closure on operations, and we have this closure operator on relations, which is also very nice and appears computer science, and for example, in case. And just final picture about this Galois correspondence. So we have this one-to-one correspondence clones. Here we have part you see clones, in the right-hand part you see relational clones. And this is one-to-one correspondence versus the order. Okay, so clones are really wonderful. But, and now the first part of my talk, phantom problem. We have a problem. If you are on domain of size at least 3, then we know that we have uncountably many clones. But we still have many results. Like, for example, we know all maximal clones for 3-element domain and for general case. We even know all submaximal clones for 3-element domain. Look at the atoms of this lattice. Then all minimal clones were classified by Eva Rosenberg, and on 3 and 4-element domain, we even know and these results were obtained using a computer, we even know all minimum clones. So we know something. But can we actually describe everything or significant part of this in the same way as we did for Tollman domain? Can we obtain something similar to the post-lattice? For example, can we choose some maximal clone and try to describe everything that's below? And sometimes this problem is very easy. For example, if you consider maximal clone of linear operations, then this sublattice is finite and very simple. And this is another nice exercise for any student. But if you consider a maximal clone of quasi-linear operations, already here we don't have a complete description, but we know that this sublattice is countable. And we know that in all the remaining cases, this sublattice is uncountable. So it means that we have continuum everywhere. And it means that if we want to get a complete description of something, we should know how to describe this continuum. And the second part of my talk, attack the continuum. Let's consider maximal clone of self-dual operations on Tillman domain. This operation preserving this one relation, one permutation. We know that, yes, this is a maximal clone, and we know from 1983 that we have continuum clones of self-dual operations. But somehow in 2010, I managed to describe all clones of self-dual operations. And this is surprising because we have continuum of them. And this is my result. To convince you that this is a complete description, I just want to show you some pictures, and these pictures were shown by Albert 2 weeks ago. So here you can see the latest of all clones of the operations on Friedman domain, and here with these two ellipses, there is continuum somehow hidden. But I want you to believe me that in spite of the fact that we have continuum here and I have a complete description, I can solve any, like I can check the clone is anti-related, generated. Okay, convince you I will show like this ellipse is finite and this ellipse can be drawn like this, but I decided not to put it complete. Okay, so we have a complete description for clones, even so this lattice is uncountable. Okay, next part. Dimension of the continuum. What we know? We know that if we have a clone containing majority operations, then this clone can be defined by binary relation. And on Feldman domain, we have only 2 to the power 9 binary relations, so not so much. And that's why computer can easily work with it. And that's what we did. Using a computer, calculated, and finally we found all clones on Feldman domain containing majority. Turned out that it's almost 2 million clones like this. Then we did even more. We were lucky and we managed to find all clones definable by binary relation. Not all of them contain majority. And finally, coincidence that the number of clones definable by binary containing majority is exactly this. 161,000. Anyway, we found this many clones. And this is somehow very bad because we understand that by binary relations, we define some fundamental properties. And even using these fundamental properties, we can define more than 2 million clones. It's too much. And we will never understand this many clones. We will never draw a picture with these clones. And we don't have a hope to draw something similar to the post-lattice. Okay. But probably this lattice that we want to draw is just too big for human brain, just too big for a paper, but probably computer can somehow calculate this lattice. And if computer can actually get this lattice, then computer should be able to solve the following decision problems. By given set of operation, given relation, decide whether they define the same. If you have a complete description of all clones, you should be able to solve this problem. For example, for Tollman domain, for my lattice, you can solve this problem easily. Given relation R, decide whether the clone defined by this R is finite. Another nice question. And problem 3, given a set of operations, decide whether the generated clone is finitely related. Like given a finite algebra, decide whether this algebra is finite. Okay, so I believe that if we get a complete description, we should be able to solve these 3 problems. But unfortunately, in 2019, Dmitriy showed that problem 3 is undecidable, and it's really bad. It was a disaster for me. I still don't want to believe that it's true, because if this is undecidable, then no way we can get a description which let us solve these problems. Okay. And now we have a hope, finally, after this terrible result. What if we, okay, not all clones are really different, because if you consider clones generated, for example, by conjunction entailment domain and by maximum entailment domain, these clones are actually almost the same. You can build an isomorphism. And if you consider clone generated by identity and operation x+1, these two clones are also very similar. So the truth is that many clones are very similar, and if you want to describe all of them, and okay, if you cannot describe all of them, then probably we can describe them modulo some equivalence relation. Okay, and what can it be? The most natural one is clone homomorphism. So if you have two clones, C1 and C2, then clone homomorphism is just a mapping from C1 to C2 that maps projections to projections and respects composition. Very natural. And it's also very nice because we have this theorem by Barta, Oxshall, and Fisker. And we know that we have this clone homomorphism if and only if relational structure defined in C1, PP interpret relational structure defined in C2. I really don't want to explain this definition, but the idea is that for clones, we have relational clones, and we have very nice Galois connection. And here, we have this clone homomorphism, but we still have something very nice on the relational side. We know that we have this homomorphism if and only if R1 PP interpret R2. Or equivalent condition is that any set of identities satisfied in one also satisfied in. Okay. And then we may consider clones up to this clone homomorphism. The equivalent, if we can map in one direction and in another direction. Okay. It's very natural to take some lattice and try to collapse this lattice using this clone homomorphism. And we did this. And we actually proved that if we collapse modulo this clone homomorphisms, this lattice is still uncountable. So the truth is that the whole part in the left-hand side, or in the right-hand side, still the same, stays the same. And what it means, if we want our lattice to be countable, we need a stronger tool to collapse. Okay. And as Albert said 2 weeks ago, we have it. It's minor preserving map. So we want a mapping from one clone to another that respects minors. So it respects permutation of variables, identification of variables, and so on and so on. We are not talking about composition, but we want to respect only this, which is also very natural and nice. And here we also have a nice result by Barta, Oxshall, and Fisker saying that we have minor preserving map if and only if R1 if we construct R2. Here you can see the definition, and again, I don't want to explain it, but the idea is that this is very natural mapping, very natural notion, and we still have something very nice on the relational side. Okay, and let's read this third condition. We have minor preserving map if and only if any finite set of minor identities, so identities like this, that are satisfied in one is also satisfied in. So whenever we cannot map, there should be some identity forbidden. Okay. Let me give you an example. Just consider this clone of monotone operations on entailment domain. Very simple clone. And another clone, 2. Clone of operations in entailment domain preserving this one direction. I claim that this M is minor equivalent to M intersection B. In one direction, this minor preserving map is trivial, just identity, because one clone is smaller than another. Let's build another minor preserving map. Let's build a minor preserving map from M to intersection M and B2. And this mapping is very nice and natural. It's like this. Take operation, disjunction, this is your operation. Here by this bar, I denote negation. And you can easily check that this mapping, very nice mapping, is actually minor preserving map from M to M intersection. So that's how we prove that this and this are equivalent. Okay. Let's go on. This is done by Albert Vukay and Manuel Badirsky. They took postulates and they collapsed these postulates using minors. And that's what they did, they obtained. And it's amazing that, okay, this is a smaller lattice. And in this lattice, we still all the fundamental properties that we had in post lattice. What we had in post lattice? We had this infinite chain of new unanimity operations. Here we have the same. We had the minority operation, majority operation. And here we also have them. So we kept all the fundamental properties, but now it's a smaller lattice. And it just confirms that this notion is very nice and very natural. So we kept all the properties, but it's much smaller. Okay, another example is my lattice of clones of subdual operations on three-element domain. And together with Albert and Manuel, we collapsed it to this also small and nice lattice. And again, we kept all the fundamental properties, but this continuum collapsed in just one concrete element here. Okay, so it's really wonderful. Now we have a very natural notion, and we continue disappear, and everything is much more simple. Okay, but it turns out that not everything is that good. We have bad examples, or at least I think that they're bad. And let me give you one of these examples. Let's consider the relation on two-element domain on 0, 1, and this relation on 1, 2. Okay, and this is less than or equal relation. And then using these three relations, considering them on three-element domain 0, 1, 2, I can build clones, TMN. For every M and N, I build a clone. Very easy. And I can prove that for any M and N, for any integers, these clones are different, modular minor preserving maps. And this means that if we want to draw a lattice of all clones, for example, on three-element domain, in this lattice, we should have this sublattice. And this is only one example, and of course, I can make it more complicated. And on four-element domain, I can make it much more complicated. So for me, this means that we shouldn't expect to draw a picture as beautiful as post lattice, because still in this picture, we should have this and something that can be built above. Okay. Nevertheless, last part of my talk, but the largest part. Let's take our computer results, how we found 2 million clones defined by binary relations on three-element domain. And we can check that 1.6 million of them are idempotent clones. And now we have 1.6 million idempotent clones, and we can try to collapse them. Of course, it's too many to do this by hands. And Libas student tried to do this on the computer. And just using second PP power, he managed to collapse this 1.6 million into just a bit more than 1,000. Then using inner automorphisms, we collapsed it to 300. Then we played a bit more using visual inclusion and so on, made it 293. And for me, this is already a small number. Like we can do this by hands. And that's what I saw. We can do this by hands. And I started to draw and to solve and to find identities. You can see that here every clone is defined by some relations, and I try to distinguish them by some identity. So altogether, we worked a lot on this. But then, unfortunately, okay, not unfortunately, then Florian joined the project. And as usually, machine beats human. And he wrote two programs, actually. One searched for collapses using even 27th power, and another program searched for identities to distinguish the remaining clones. And using these two programs, Florian managed to collapse the remaining clones. And as a result, we obtained 133 different clones defined by binary relations up to minor preserving map. and this +1 is just clone of all operations or clone containing constants. Because here we considered only idempotent, and we have only one non-idempotent. Okay, so we have exactly 134 clones modular minus. And this is a really small number. Now we can look at the result we obtained. And now I will try to give you even more examples. Okay, you have plenty of time probably. The top one, clone of all operations. The next one, as in Albert's talk, clone of all idempotent operations on element domain. Okay. How to prove that they are not equivalent? To prove that they are not equivalent, we should show an identity satisfied by all operations, but not I3. And this identity is very simple. It's clear that this identity can be satisfied only by constant. And that's it. Okay. Then what's below I3? It's B2. B2 is defined just by this relation, and it's clear that B2 doesn't have multi operation, but I3 does. Yeah, here you can see just definition of multi operation, or you may say quasi-multi, because here I write f of y instead of just y. Okay. C2, clone defined by this. And this C2 is actually clone on two-element domain, and this is also clone on two-element domain. And this is one of the advantages of considering minor preserving maps and clone homomorphism, because we now can compare clones on different domains. Okay, so this is C2. C2 doesn't have two cyclic operation, symmetric binary operation, I has. And another one is C3, which doesn't have three cyclic operation. And 2 weeks ago, Albert presented this result that we have only 3 sub-maximal classes in this poset. Okay, but we can go on. Meet of these two clones is this, B2C2. Meet of these two clones, C2C3. Here you can see the relational definition of contained clone on the domain. Meet of B2C3. And I use the same colors for the edges. So you can see the C3 and B2C3 are different because this one has no malser, red color, and this one has. Okay, let's go on. Another clone. This is a clone of operation preserving this relation, 0, 1, and 2. And preserving this one binary relation, 0, 1, 1, 0, 2, 2. And you can easily check that this one has no symmetric majority, and this one has. And so on. Another nice clone, another nice clone. And everywhere on the edge, you can see a concrete identity showing that they're different. Wonderful. And that's the whole lattice. And yeah, again, I want you to believe me that if you just look at these clones, at these concrete classes, they're very nice, not just random choice of some relations. And when we try to find nice identity, we also did a lot of work, and sometimes we actually discovered something very interesting. Okay. Yeah, let me show you a bit more. A small part of this lattice, which I consider very interesting. If you consider clone of monotone operations on two-element domain, yeah, and now we are on two-element domain in general. This is a clone generated by disjunction and conjunction. We consider only idempotent clones now. We already proved that this clone is minor equivalent to M intersection B2. Okay. And consider another clone generated by majority operation on two-element domain. So we have these two clones from post lattice, and we know that we don't have anything between them on two-element domain. Okay. And now I want to show you the situation for three-element domain. What we have between them for three-element domain. Okay. And yeah, of course, the operation, the identity showing that they are different is two cyclic operation. We don't have two symmetric operation generated by majority, but of course we have even two disjunction and conjunction. Both of them satisfy this identity here. Okay, this is on 2-element domain. And what do we have on 3-element domain? Okay, now our domain is 0, 1, 2. It turned out that it's 1.3 million clones on the 3-element domain that are equivalent to 1. And this is the largest class of clones. So from this 2 million, 1.3 million are equivalent to just this one, which is kind of nice. And the second popular clone is this one, clone generated just by this majority. It has 93,000 clones. Okay, and on 3-element domain, we have 3 classes in the middle. And you can also check the definitions. It's kind of easy and nice. And now I want to show you why all of them are different. Here, you can check that M contains, again, 2 cyclic operations like conjunction and disjunction, but this clone does not, because it has this 1, 2 to 1 relation. It's like 2 cyclic operation blocker. Okay. Here to prove that these 2 clones are different, yeah, we can check that majority, the clone generated by majority, doesn't have this operation. Metric operations, it finds this identity. Why is this true? Because if you have majority operation, then the only symmetric 5-array operation is also majority. And majority doesn't specify this identity. And here you can easily find such an operation. Okay, and so on. Here we choose 2 cyclic plus minority. So on the first 2 variables, it's symmetric 2 cyclic. On the next 3 variables, it's minority. And this distinguishes these 2 clones. And another nice identity distinguishes these 2 clones. Okay, that's the picture we have somewhere in the middle. And in my opinion, it's also very nice. You can play with concrete examples of clones. Okay. And now the whole picture. This picture was generated automatically, but still it's kind of nice. I can show you some parts of this lattice. You can see exactly 133 clones. And like these are 3 submaximal clones Albert was talking about. Okay. Okay. And another, Albert would say that it's a disappointed result, that this is not a lattice. And this is probably the first claim we can derive from our computer characterization. That clones on 3 elements, modular minor preserving maps, do not form a lattice. And I will try to explain this result. Again, we consider this clone of monotone operations on 2-element domain. And we consider this clone. Yeah, it already appeared today. Clone of our operation preserving this binary relation and preserving this equivalence relation. These 2 clones have one meet and another meet. And you can easily check that all these 4 clones have majority. And what it means, if join of these 2 in the bottom exists, then this join should also contain majority. And since this join contains majority, it should be in our lattice and in our classification, because we took all the clones definable by binary relations. So we took all the clones definable by majority, and it should be in our lattice, and it's not. So you cannot find join of these 2 in our lattice. Originally, I wanted to prepare a non-computer proof of this claim, but somehow I failed because I wanted the proof to be nice and simple, and I could not find it. But I will try to explain why it's expected, it was expected, and it's not that bad, that we don't get a lattice, modular minor preserving maps. Okay, if you look at this left bottom clone, it contains an operation which is semi-lattice here on 0, 2, semi-lattice here on 1, 2, and minority on 0, 1. So on 0, 1 is just like this. And the right clone is an operation which is minority here, like Z2 here, and majority between 0 and 1. And both of them has this operation. Semi-lattice here, and majority here. And also all of them contains majority. And now imagine that we want to calculate a join of this and this. And this join should be still in our lattice, so it should be still on 3-element domain. And somehow it's just impossible to, and okay, we can write identities corresponding to this operation, to this operation, to this operation, and to majority. And then in join, all these identities should be satisfied. And it turned out that it's just impossible to satisfy them unless you have a very symmetric operation. Like this clone contains minority, proper minority, and this clone, of course, contains proper similarities. So you cannot take these a bit ugly examples and feed them into one concrete clone on the element domain. To feed, you need to have something symmetric. And that's why it's really expected, and that's why I don't think that this is a very bad sign. But of course, since this is not a lattice, we shouldn't expect to find a nice global connection just for clones on the element domain. But still, I believe that if we consider clones on any finite domain, then this should be a lattice. Okay, and yeah, our big goal, of course, is to characterize all clones on element domains model minor preserving. And we have a plan, and we already did a lot in this plan. So first, we classified all clones of the operation model minor preserving maps. That's done. Also, we can take all minimal Taylor clones and characterize them on the minor preserving maps. It's also done. Take 1.6 million clones defined by binary relations and characterize them. It's done. Find all submaximal elements in the poset. Done. Now we need to find all sub-submaximal, what Albert is working on now, classify all multiples of clones model minor preserving maps, and so on and so on. It's probably a big plan, big road, but I believe it's really doable. And why I think this would be very nice. Imagine that we have a complete description of all clones, model minor preserving maps. What would it mean for us? Would it mean that we get a beautiful picture? Now I don't really believe in this, but hopefully we get something. But more importantly, we would get like a handbook of clones and H1 identities on element domain. So imagine that you can answer any question like, can we generate majority from 3 cyclic and multiple? You can just open this handbook and check that, yeah, this is true or this is not true. And also it's a source of many, many examples of finite algebras. And of course, there are a lot of cool problems. For example, what you can do, you can take any minor class and you can calculate the number of clones there. And it can be either finite, uncountably many, or countably many. You can try to describe all clones satisfying some set of H1 identity. You can try to generalize this result for larger domains. So it's a source of many, many different problems, and it gives us a lot in understanding of the element domain in general. Okay, so it would be really nice to have this description, and I hope that we will do this, and I invite everybody to join our big work. And that's it. As always, I was probably fast. Sorry for this.